We're going to talk about Rolle's theorem. Michael Rolle was born in 1652 and he was a French mathematician, and he's known for Rolle's theorem that we're going to talk about today, published in 1691. He's also a co-inventor in Europe of Gaussian elimination, and an interesting thing about him was he was a vocal critic of the calculus methods in his day, and he said they were a collection of ingenious fallacies. But later he did become convinced of the correctness, was a firm believer in calculus. Rolle's theorem states, let f be a function that satisfies the following. The first thing is f is continuous on the closed interval from a to b. The second thing is f is differentiable on the open interval from a to b. And the third requirement for Rolle's theorem is the function at a needs to equal the function at b. If we meet these conditions, then there's at least one number c in the open interval from a to b such that the derivative at c equals 0. So let's look graphically to see what this theorem says. So here we have a function on a closed interval from a to b, and it is continuous there, and it is differentiable, and the function value at f of a equals, as we see here, the function value at f of b. So Rolle's theorem tells us that there exists a value c somewhere on the open interval from a to b such that the derivative equals 0. A couple of cases, actually there's 3 cases that we want to consider. The first case is if we have a constant, and we can see if we have a constant that's going to be easy because the derivative equals 0 everywhere. We could have the case where we start at f of a and we need to end up at f of b equaling f of a, and so if the function increases, since the function increased, the only way we can have this continuous differentiable function is if it then decreases to get back to the value it started at, since f of a equal f of b. So somewhere it has to turn, and it would have to have a maximum where they have a horizontal tangent where the derivative is 0. Now if the function did more than one turn, that would work as well. If it increased and turned, it could also go below that original function value, but then it would need to turn to go back because f of b needs to equal f of a, so there would have to be at least one place, could be more than one place, where there was a horizontal tangent where the derivative equaled 0. If the function just simply started by decreasing, again it would have to turn somewhere to increase to get back to the original function value. So let's go ahead and look at the proof. We're going to look at 3 cases. First of all, when it's constant, and that one's going to be easy because then the derivative equals 0 everywhere because it's a constant. And so on the open interval from a to b, c could be any number because every number has a derivative equaling 0. So Rolle's theorem is proved easily for a constant. Now let's look at the case where for some x on a to b, the function value is greater than at this endpoint. So again, we say since the function value went greater, somewhere it's going to have to turn to get back down to f of b, and we can state then that f has a maximum value somewhere on the interval from a to b, and the reason we can state that is by the extreme value theorem, because the extreme value theorem said we need a continuous function on a closed interval, which we have, so it guarantees us that it takes on its maximum and its minimum value somewhere on that closed interval. Well, we know that that would have to happen at a place where the derivative is 0, the place doesn't exist, or at an endpoint, because of the extreme value theorem. Well, it's not going to happen on an endpoint because we said there is somewhere where the function value is greater than the endpoints, so it's got to happen somewhere between a and b, and so there does exist a c such that that is true. And so at this c, we know the derivative equals 0, and we know that because of Fermat's theorem. And Fermat's theorem basically told us if we had a function and there was an absolute maximum or an absolute minimum, if it was a continuous and differentiable, that the derivative equaled 0 there. Looking at the third case, it's very similar to the second case, but now we have the function less than f of a somewhere. So if the function went less than somewhere, we can again apply the extreme value theorem and know there had to be a minimum somewhere on this interval from a to b, and actually this should be on an open interval because it's not going to occur at the endpoint, since we know there is a function value there somewhere where it is less than f of a. And again, by the extreme value theorem then, we know that there exists a c on the open interval from a to b where it equals this minimum value, and then we know that that derivative at that value c by Fermat's theorem equals 0. Now, what's going on here? We have this closed interval from a to b, but there is no place where there's a horizontal tangent where the derivative equals 0, and that is because we don't meet one of the conditions of Rolle's theorem. We don't have the continuity, and that's one of our requirements for Rolle's theorem. So no guarantees of the derivative equaling 0 here. Continuous is important. Okay, let's look at this one. We've got a continuous function on the closed interval from a to b, but there's no horizontal tangent again, and we do not have it differentiable. And so that's an important condition as well. Number 2, it has to have that requirement of differentiable to guarantee that there's at least one number c where the derivative at c equals 0. Let's find an interval on which Rolle's theorem applies to this function, and then we'll look for all points on the interval where we know the derivative equals 0. So as we look to see if Rolle's theorem applies, we need a continuous function on a closed interval. And as we look at this function, it is a polynomial function, so we know it's continuous everywhere. We're going to need to find a closed interval that meets condition number 3 in a minute here. So we're going to be looking on some interval from a to b, and we're going to need to decide what those values are. Condition number 2, it needs to be differentiable on the open interval from a to b. Since we have a polynomial and we know polynomials are differentiable everywhere, we've met that condition. And then condition number 3 is f of a needs to equal f of b. So we're going to need to find an interval where this is true. Looking at the function, I see that there's an x in common, so I'm going to factor this function. That'll help me to decide what to use for my a and b. And that factors some more, so that's going to factor into these factors. So it looks like the function, and maybe the easiest place, is to figure out where this equals 0, and the function equals 0 when x equals 0, 5, or 2. So an interval from 0 to 2, 2 to 5, or 0 to 5 would meet the conditions. Let's pick 0 to 5, make this a little more interesting here. So we know we've met condition number 3 because f of 0 equals f of 5, which equals 0. So Rolle's theorem applies, so we know on this interval from 0 to 5 that there exists a c somewhere where the derivative equals 0. So now we want to find all the points to confirm this. So we're going to need the derivative of this function, and that's going to be 3x squared minus 14x plus 10. We're interested in where that derivative equals 0. Looking at that, it doesn't look like it factors, so let's use the quadratic formula. Negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. See if we can simplify that a little bit. 14 plus or minus square root of 14 squared minus 120 is 76 all over 6. 76 is 4 times 19, so we've got 14 plus or minus square root. The 4 comes out in front as a 2. The 19 is still under over 6. We can now reduce all of these terms by a 2. So we'll have 7 plus or minus square root of 19 over 3. And we could put those in a calculator and get decimal approximates. We need to confirm that they fall between 0 and 5. We know by Rolle's theorem at least one of them does. If we do 7 minus the square root of 19, that quantity divided by 3, we get about 0.88, and that's on our interval. 7 plus the square root of 19, quantity divided by 3, we get about 3.79, and that's also on our interval. So Rolle's theorem guaranteed that we had a value c on this interval where the derivative was 0, and we actually have 2 of them. So here's our interval 0 to 5, and our first value was 0.88 where we've got a horizontal tangent, and our second value 3.79. There's a place where the derivative equals 0, guaranteed to exist by Rolle's theorem.